All right, chemistry students, welcome to your new unit, Unit 5, on chemical reactions. So these are your notes for chemical reactions. That's what we're going to start working with. You're going to see today we're going to fill out this first section right here. And then we're going to end up flipping the page over actually and talking a little bit about diatomic elements and states of matter. So we'll start off with the first part. I know it's kind of in a weird order, but just go with it. The first part, let's hop right in. So a chemical reaction is when different molecules and atoms and compounds all change. Chemistry is really all about change. It's one of my favorite quotations from Breaking Bad. Is how chemistry, it's not really about atoms and molecules or matter. It's really about change. And so anytime that chemical bonds or electrons change, that's a chemical reaction. And we show these in a chemical equation. So a chemical equation shows all of the chemical species involved in the reaction. It tells us what we start with and what we end with. And it's usually written as in formulas like an equation, but it can also be written as a sentence. So I'm going to give you an example. So calcium chloride reacts with sodium sulfate to produce calcium sulfate and sodium chloride. This is a chemical reaction. It's a chemical equation in word form. So if you read this, what it's describing is how this compound, calcium chloride, reacts with another compound to produce or make, to form two other chemical species. So in this particular case, calcium chloride, sodium sulfate, and sodium sulfate, or sodium chloride, pardon me, are the chemical species. It's a convenient word that just generally means all the chemicals involved in a reaction. Specifically, the reactants are, so if we, sorry, we'll take this back a second. We can say this verbally, but we tend to write it out as formulas instead. So this is the chemical equation. And this is writing out this information, but in a way where all of the compounds are written out for us and such. So calcium chloride plus sodium sulfate gives us, the arrow you can say in a couple of different ways. You can say yields, which means like produce. You can say produce, you can say form. All of those are words that mean this arrow. The arrow is kind of like an equal sign in math. So we have what we start with, some change happens, and this is what we end with. We call these the reactants, and we call these the products. So these are the things that the species that react. These are the species, chemical species that are formed or produced. They are the products. So that's that. A couple other things you'll notice about this is that we have to write out the correct formula. So calcium chloride, sodium sulfate, calcium sulfate, and sodium chloride are all ionic compounds. And we have to write the formulas correctly. That's very important. So all that's there. That looks super familiar. There's probably a few things on here that are not familiar to you. The first would be these little letters in parentheses after. We're going to talk about those today, but those are the states of matter. So that tells us what state of matter each of these chemical species is in the reaction. It's good for you to know these, and at a certain point, I will expect you to sort of be able to predict what state of matter each species is in. But I'll help you, but we'll kind of go through that more near the end of the unit. Just so you know, AQ stands for aqueous, which means dissolved in water, and S stands for solid, which means it's a solid that is not dissolved in water. The other thing you're going to notice is that there's a 2 in front of this NaCl. This is something you have to do with chemical reactions. It's called balancing them. And it's to make sure that they follow the law of conservation of mass. We call this number a coefficient. So these little numbers down here are your subscripts. So subscripts refer to the element right in front of them. A coefficient refers to the whole species. So this 2 means that there are 2 sodium chloride compounds. But we're going to learn more about that next. Okay, so that is those notes. It's now time to flip to the back, and I am going to move to the next part of the PowerPoint. Just one moment. Okay, great. So this should be on the back. Hopefully this is what you're seeing. So we're talking about diatomic elements. Okay, this wasn't really an issue before, but it's going to be now. In chemical equations, a lot of times we are not dealing with compounds, we're dealing with elements by themselves, so just pure elements. Most elements, the vast majority of elements are just kind of standard elements. But there's a couple of exceptions. These are the Hofbrinkels. They're called the Hofbrinkels because of this acronym. There are 7 of these elements that in their elemental form are actually bonded to each other. So diatomic means 2 atoms. So a diatomic element is an element that 2 atoms are bonded together in their natural form, in their elemental form. So these are hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. Hofbrinkel. That's how I always remember it. Some people say Brinkelhof. There's nothing wrong with that, except for that they're totally wrong. It's Hofbrinkel. Brinkelhof sounds ridiculous. And Hofbrinkel sounds totally normal, right? Anyway, so yeah, what this means is that if you have oxygen, so for example, combustion reactions, or when you burn anything, it requires oxygen. Oxygen is one of the reactants in those reactions. It's a chemical species. When you write it, you can't just write O by itself. Anytime you see oxygen, it's actually O2. The same thing is true for all of these. For example, most of the atmosphere is made of nitrogen. I think it's like 70 or 74 or 75%. That nitrogen is not single nitrogen atoms floating around. Instead, they are diatomic nitrogen atoms. They're bonded together. Plenty of atoms ride solo. Most atoms do. So for example, carbon now carbon's kind of a weird one. Maybe that's not the best example. Let's think of another one. There's lots of them. Thinking all the metals. So calcium. If you have a big chunk of calcium, it's individual little calcium molecules or little atoms. They're not bonded to each other. They're just separate atoms. All of the noble gases like helium or neon, totally on their own, completely separate atoms, not bonded together. As soon as an element is in a compound, this rule no longer applies. So if you remember, we've definitely used oxygen and hydrogen and fluorine and bromine and nitrogen and chlorine in writing ionic and covalent compounds, and this does not apply. So for example, calcium oxide, the formula for calcium oxide is CaO. It is not CaO2. That does not make any sense. It doesn't neutralize properly. This is only when listed as an element, not as part of a compound. So that's diatomic elements. There are also 2 other weird ones. Those are phosphorus and sulfur. If you find phosphorus by itself in nature, it is actually P4. So there's 4 phosphoruses bonded together. If you find sulfur in like elemental sulfur, it's actually these little octagon rings. It's kind of weird, but there you go. This you can write on your periodic table. So I'm going to grab my periodic table real quick, and I'll show you this. Unfortunately, the light in my room went out, so let me just get up and turn the lights back on. 1 second, so you can actually see. There we go. Okay, so I'm going to recommend you can do a couple of different things, but it might not be a bad idea. I'm actually just going to kind of do a little box around all the Hofbrinkels, or put a little star next to them. So we've got hydrogen, put a little star next to it, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. And then sulfur and phosphorus. Just little stars next to each one, just so I can remember that these are sort of special. And I'll put double stars next to phosphorus and sulfur because they're like really special. Okay, so that's how you can remember the Hofbrinkels. If you even want to just write, let's see, I don't know where, oh, here's my pen. If you even just want to write like maybe on your periodic table somewhere, just to remind yourself, just write Hofbrinkel, and that way you'll remember. If you make this mistake in class, it's super, super common. I will just yell Hofbrinkel at you. I have this habit of wandering around the classroom, looking at people's work and going, Hofbrinkel, Hofbrinkel, Hofbrinkel. I mean diatomic. I mean that you've made a mistake there. Hofbrinkel. I'm gonna underline Hofbrinkel here. Okay. Next thing is the states of matter. So we're on the back page of the notes, diatomic atoms, Hofbrinkel, etc. You'll notice that, yeah, something like zinc or iron or I don't know, what else? Carbon, those are not brinkles. I had a student who called them a not brinkle once, and I thought that was kind of cute. Those are not Hofbrinkels. They're just by themselves, but oxygen is that way. Okay, let's talk about states of matter now. We're going to go into this a little bit more. We've got this notes on solubility that you can kind of see right there, but we're not going to worry about that quite yet. Just so you know, this is what each of those stands for. So S is represents a solid, L is a liquid, G is a gas, and AQ is aqueous. So if you guys want to jot those down as well, most elements, almost all the elements are solid in their natural form. So all the metals are solid. There's a few exceptions, but there's not that many. And all ionic compounds are solid. So think about like salt, you know, table salt, that's a solid. And most ionic compounds are just like table salt, they're all solids. Liquids, mercury is a liquid. It's a weird one. So is bromine, water, and a lot of covalent molecules. So things like alcohols are all liquids. What else is liquids? Some covalent molecules are gases like methane or ethane, which are CH4 and C2H6 respectively. Propane, which is C3H8, is a liquid. I think, or maybe it's a gas. It's kind of in between propane tanks. I can't remember. I think might be a gas. Butane is a liquid. That's what's in lighters. That's C4H10. And you know, gasoline is pretty much a liquid. It's kind of, but it vaporizes pretty quickly. Acetone is a liquid. So those are some examples. Gases, all the noble gases and most of the Hofbrinkels, except for bromine and iodine. Iodine is actually a solid, kind of interesting. And a lot of some other molecules are gases, depending on the temperature. And finally, aqueous is any solid that dissolves in water. So if something is normally a solid, but you dissolve it in water, like salt. If you have salt water, salty water, that would be aqueous. So you'd say NaCl aqueous, AQ meaning dissolves in water. Okay, so those are all things that you might see. So I just want to make sure that you all have that. We are going to have some more notes, but in the meantime, let me show you. I want to go to my YouTube page. All right, on my YouTube page, you can see I have a bunch of videos here. I would say this one is something you should definitely watch, The Law of Conservation of Mass. Actually, we can watch that one later. Here, this one's kind of good. The How to Write Chemical Equations from Word Descriptions. It's a bit long, but if you want to know more about how to write chemical equations, that might be helpful for you. I think we might go over that more a little bit later. Speaking of, let's take a look at your unit packet. And that might give us some really good hints about what you can work on. Actually, your first page of your unit packet is balancing chemical equations. So we're not even there yet. That's coming up pretty soon. So we'll come back to that. So there you go. So that's all you need to do for right now is take the notes. The next thing, oh, I do have this. The next thing that we're going to do is our lab simulation, which is called Balancing Act. It looks like this. And again, I've got the link here. It's one of those PhET simulations. So that's the next thing that we're going to do to help you learn about balancing chemical reactions. All right. I'm going to stop there. I will see you in the next video when we officially go over balancing chemical reactions. Until then, enjoy your chemical reactions and this whole wonderful chemistry unit.